Hi, Chem students. A lot of the things that we see as physical processes, that we talk about as physical processes especially, are the phase changes that occur between pure and even mixed states. So, for example, the big four that we're going to talk about at all time will be the solid, liquid, gas, and possibly the plasma phase, even though plasma has been kind of pushed out of most textbooks. So I'd like you to know what each of these transitions are, these special transitions like evaporation or vaporization. We've spent a lot of time talking about that liquid to gas transition. And we also talked about the opposite of that, the gas to liquid transition. And they're summarized right here as being vaporization or condensation. So the same thing goes for all the others. You should know all the names of these. So this is evaporization, or even just vaporization, however you want to say it. And of course, this is condensation. The ones that most people miss have to do with the solid and the gas phase. If a solid turns directly into a gas, then we call that sublimation. And then if a gas turns into a solid directly, we call that deposition. Now just think of this. Sublimation is something is sublime if it's kind of vague or hazy. If you go from a very concrete, solid object where you know exactly where it is to a vapor, that's a very sublime change in the sense that it's gone from this concrete to the vague. So that's where the sublimation comes from. The deposition, the idea is that the gas is depositing itself on top of the other molecules to make the solid. So that's the whole concept behind it. Now, since we have these phase changes, we should think about how they occur, what's happening in them, and we can kind of map out the energy changes that are going on by a thing called the heating curve. So what we're going to do is we're going to add some energy, and if we do that in a constant basis, then the time that we take will tell us essentially how much energy we're giving. So that's why the axis here says time. And then we can just measure the temperature and watch what happens. So what we're going to do is we're going to start with a solid. Start with a solid way over here, part A. It'll be some kind of cube of some sort. It might be, if this was water, be an ice cube. But whatever it is, it's some kind of solid. And we're going to add this energy. And as time goes on, the temperature will increase. You can see that right here in the curve. The temperature is going up right here. But why is it going up? Well, that's going up because the translational kinetic energy must be increasing. So the energy that we're adding is at least partially going into the translational kinetic energy. But something odd happens here at point B. At point B, we stop seeing that change in the average translational kinetic energy. That no longer changes, it becomes constant. So our energy is going into something else. So here there's no temperature change, there's no change in temperature, so our energy, we think, is going into potential energy. And what we imagine is happening here is that we've started with this block of stuff, but over time, as we go from B to C, point C will be some sort of puddle of liquid. And in between, we can even imagine a smaller cube in the liquid. So this is point C right here. So that energy has gone not into making things move faster, but into loosening the IMFs that hold that solid together. Right, at this point then, at C, we're continuing to add the energy, so we see an increased temperature, which implies there's an increased kinetic energy. And then we get to point D here, where we've got a liquid. So we've got some liquidy substance here. And when we get done, what it's going to look like is a gas. And in between, at some other point, we're going to see a smaller bottle liquid with some gas over it. And what's happening here? Once again, there's no change in temperature, so we must be putting our energy into the potential energy. What potential energy? Here, we're going to break the IMFs. We're going to overcome them completely. So that's where the energy is going. Now, what's interesting about all this is what would happen if we were to run the same experiment, identical experiment, start with the same type of substance at the very beginning, the same amount of substance at the very beginning. What if we were to run this now under different conditions? For example, what if we were to actually take this substance and do the same experiment with a larger external pressure? If you think about it, if we push down on something harder with more force and from the outside, we could take it and we can make it, it's easier to condense it. We're more likely to get a condensed phase. So the temperature at which we make a solid will be higher. So this liquid to solids, here we got liquid and here we got solid. This liquid to solid line here from B to C will actually be a little higher. So it's going to liquefy, so the liquid's going to solidify a little bit earlier. It's also at the same time going to liquefy easier. And so we're going to see this will be slightly different. These changes, we can imagine this could be experiment 1 and this would be experiment 2. We would get a pressure and a temperature for boiling in this case. And here we'd also get a pressure and a temperature for boiling. At the same time, we'd get a P and T and a P and T for freezing, both for melting or freezing, however you want to whatever you want to call that. If we were to do this over and over and over again, we might be able to see an interesting phenomena. So if we look at just these boiling points, melting points, and sublimation points, what happens if we put those onto a graph? Let's take a look. What we have in hand are for boiling and for melting and for sublimation. We're going to have these pressure and temperature combinations. As we change the pressure, the temperature at which we boil changes. We change the pressure, the temperature at which we melt changes. We do the same thing over here. And we take a whole bunch of these, and now let's put them on the graph. So let's start with the sublimation, and let's just put that on the graph. And what we're going to find is that sublimation kind of happens down here on this graph, this pressure versus temperature graph. All right, so we put that on there. We notice that at some point we stop seeing any ability to sublimate at all. So now let's look at the melting data, and let's plot it. And for most substances, it's going to look a little bit like this. So this line right here is for melting. This line right here is sublimation. We only have one more set of data put on here, and we're going to put our boiling or evaporation, however you want to call it. We'll call it boiling. So what's happening here is we've now mapped out these transitions, and it turns out that if we take a good close look, this is melting, solid going to a liquid. This is solid going to gas. So anything to the left must be a solid. Up here, this is solid to a liquid. So anything in this region is going to be a liquid, and anything in this region is going to be a gas. And of course, when we're saying in this region, we're saying at any pressure and temperature that occurs in this area to the left of these lines, the substance will be a solid, and it'll be stable as a solid. Now, if we get right to the line and we're right on the line, then that's the pressure and temperature at which we would notice all of our energy would be potential energy. Everywhere else, if we added energy, we'd see a kinetic energy change. And we'd see a temperature change as well. So on these lines, those are when the phase transitions occur. All we've done is we've plotted where phase transitions occurred. Let's take a note of this one right here. It's called the triple point. And you can see what's kind of interesting about it is that all phases, solid, liquid, and gas, they exist at the same time and they're in equilibrium with each other. So that means what we would see in that condition, in that particular situation, is the ice cube solid part with a puddle around it and some vapor as well, and there would be some kind of dynamic equilibrium that some of the gas would turn into liquid, some of the liquid turn into gas, some of the gas would turn into solid, some of the solid would turn into gas, some of the liquid turn into solid, and some of the solid would turn into liquid. We'd see all those phase changes happening at once, but we'd end up with constant amounts of the vapor, constant amount of the liquid, and the constant amount of the gas, all the solid, all at the same time. So as we just saw, there's a kind of a characteristic shape to these phase diagrams, and that's what we really want to know. However, it's kind of cool to know that there's a few substances, and one of them being a very special one, water, others being plutonium, I think arsenic, there's a silicon compound of some sort, but there's very few that are different in the sense that they don't have the same exact look. But they look similar. Here's one right here. Let's take a kind of a look at of a scaled look at water. We still see the solid to gas look the same, and the gas to liquid look the same. But what we notice that's different is there's a negative slope to the solid and liquid transition. What's so special about this is it's one way, one viewpoint of how you can explain the ability to ice skate. So imagine we're here at this pressure and temperature combination, and this is normal, the normal situation for us, where we've got some solid ice, let's say on a lake, and when we put our blade of our ice skate down, we have an instantaneous change of pressure. Now the temperature outside hasn't changed just because I put my foot down onto a piece of ice. However, by increasing the pressure, as you see, we've forced a little bit of the solid water to turn into liquid water. And so this phase transition that occurs underneath your skate is what you slide upon. You slide upon the liquid that's on top of the solid. At least that's what some people say. Others are arguing about that at this right now. That's not 100% certain. So, but that's what most people believe. This explains why if we built this phase diagram for something like methane, solid methane, we could not ice skate on it. Why? It would have, instead of a negative deviation, this kind of regular deviation, and so if the pressure did increase, we would stay in the solid region. So this would be something more like what we'd see for a solid methane. If you may have noticed, this is kind of left empty over here. Let's take a look at another version of one of these phase diagrams. That's what this is called, a phase diagram, and see if we can find out what that is. So here's another picture that, of course, I've borrowed from the web that shows a fairly reasonable phase diagram, pressure and temperature shown. And if we look here at that particular point on the line here, on this line, the red line right in here, that, of course, is where we said we're going to see boiling or evaporation happening, essentially. And if we do see that, we have both phases, liquid and gas. And so we're going to see the meniscus. See the meniscus there? Well, it turns out that once we get to a certain pressure and temperature over here, anywhere in this region, anywhere in here, we call it supercritical because we don't have a substance that now has either the properties of a liquid or a gas, but shares the properties. For example, the meniscus is gone. Do you see a meniscus in there? I don't see a meniscus anywhere in that little region. And so the meniscus is gone. Yet it doesn't behave just like a liquid. It doesn't behave just like a gas. So they call this a supercritical fluid because they really don't have any other way to describe it. So the pressure is such that it would like to be a liquid, but the temperature is such that it would like to be a gas. So these two things are at odds, and we get a very odd behaving substance. So special points, once again, the triple point, any point on one of the lines is a phase change, and then the supercritical region. That's the kind of things you should know for a phase diagram. A phase diagram, which will always be a pressure versus temperature graph. There you go. I hope that helps you a little bit with your studies on the phase changes of pure substances.